but I normally don't take any points off. You're still going to get a really stupid small probability. You would just get a little bit stupid smaller, right? But that's the whole point. Either way, you're going to get a very small probability. It's more likely the guy did it then, rather than we just all randomly picked it. Cool? You guys ever heard the story about the 4 guys come in and they all said, "Oh, teacher, we're late because one of the wheels got flat, and that's why we're late to the exam." He's like, "Okay, you can come to my office. I'll give you an exam." And he puts them in 4 different rooms, and there's only one question on the test, and it's which tire blew. What's the probability that all 4 of them pick the same tire? You can do this the same way. It's the same problem. But now it's just a 1 out of 4 chance, right? So what's probably they all pick the front right tire, 1/4 to the 4th, plus 1/4 to the 4th, plus 1/4 to the 4th, plus 1/4 to the 4th, and that ends up being pretty tiny. Right? So if they all pick it, then he's like, "Oh, you guys are telling the truth then, more likely." And if they don't, you're all screwed, right? Trying to lie to me. Rah. I don't know if you guys ever heard that. It's not, it's not something that I heard a story today. So I understand. All right. Anything else? Any other questions? Yeah. 27, 4-3? 4-4. Oh, I love this problem. Okay. This is when I introduced the "and" idea, did I talk about the O-rings on the space shuttle? I can't remember if I talked about that. Redundancy, so that if one fails, the other one, the probability it fails at the same time will be so small, right? Same thing here. I really want to get up in the morning. Actually, this funny thing is I did this morning because I set my alarm, then I set my alarm on my phone so I'd actually believe the first one. Because the hour hits you in the face. Bam! And we lost an hour. Everybody realized that. By this point, you did. So the probability that one alarm clock works, what is that? This is number 27. Section 4.4, right? This is the one you're talking about, right? Yeah. Okay. So they tell me that. What's the probability one alarm clock works? 0.9. 90%. I love it. So part A, what's the probability it won't work?
1 minus 1.
So we'll say that this is A. So not alarm working, it would be 0.1, the leftover, right? So that's 90%, the other one's got to be 10%. All right, cool. That alarm clock sucks, kind of. That means, on average, every 10 days it will work 9 of them.
Kind of get you fired.
That's pretty bad, but we'll deal with that. If you have 2 alarm clocks that are the same way, 2 clocks, what's the probability that they both fail? So 2 clocks, that number 2 sets up the number of places, right? I've got this clock and this clock. What's probably the first one fails? 10%, right? What's up? Everybody all right? It's probably the other one fails. And they're independent. This clock is not going to go over there and say, "Well, he didn't work. I'm not going to work either." So they're independent. If one doesn't work, that doesn't mean the other one's not going to work also, right? Okay. So what's 0.10 times 0.10? 0.01 or 1%, 11. With 1 alarm clock, you have a 0.9 probability. What's the probability of being awakened if you use 2 alarm clocks? So here's the trick of probability. That's the question in English. We need the question in math-ish, even worse, statistic-ish, which is hard to say. What's it say? It says, what's probably the being awakened? So the mistake people make is they do the probability of both clocks working. Who are you that you need 2 alarm clocks going off? What, do you have them taped to your head? And they both, the only one goes off? What will wake you up? If what? If at least one, right? If one works or the other one, or both of them, obviously, you'll wake up. So really, what is part C asking you? The probability that at least one works. Now, what did I just say the other day about that at least one? Yes, the easier way to do it is 1 minus the opposite would be 1 minus what?
0.
Yeah, none of them working. So that's the same thing as 1 minus the probability that neither works. And then we just calculate this?
Yeah,
Yeah, up here. So 1 minus 0.01. So it must be of 99 or 99% chance. So the mistake people make is they multiply 0.9 times 0.9. That's 0.81. Why should it be worse? Why should it be a smaller probability with 2 clocks than it was with 1? That makes no sense. It should be a higher probability with 2 clocks, right? Because now there's 3 ways you'll wake up with 2 clocks. Whereas before there was just 1 way. It works, right? You guys kind of with me? Okay, all right. I like some of your reactions like, yeah, sure. Whatever you say then. All right. Does the second alarm clock result in greatly improved reliability? Well, it's probably you woke up before. 90%. What is it now? Would you say that's improved?
Yes.
Hell yeah. Now, every 100 days, it will just not work one of them. Instead of every 10 days, it won't work one of those, right? I'd say that's a pretty damn good improvement. I still say those alarm clocks suck. I don't know where they bought them. They must have cost 20 cents. Yeah.
If you don't correct your homework, do you not get credit for it?
When I say correct, you currently have half credit. Corrections, you don't have to get them all right, but you got to get enough of them right on your corrections to get full credit. Right? Okay. Yeah.
Just 30 and 4.4.
30?
Oh.
Yeah, I don't think I wanted you to do 30.
Oh.
Okay. All right, guys. Let's get into chapter 5. Yes. All right. It sounded almost like a question. We will now get into chapter 5. I've got to be careful the way I phrase things.
But 5 is not on the quiz.
No, 5 is not a quiz.
So we're not doing 4.5?
We did. 4-5 is the conditional, the given, right? Oh, yeah. Oh, I kept forgetting this real quick thing about 4-5. I was really careful the way I was writing this, and then I forgot that this book actually uses the symbol. So probably A given B. In the book, you're going to see this, A given B. That is not equal to probably A divided by. It's not a division symbol, right? It's probably A given B. And that formula is, remember that formula there that we put together? Yep. So page 173, there's that formula there. Well, we did that together in class.
This is probability divided by the probability of A.
Oh, that's B given A. You divide by whatever the given is. So it's probably a C given W. Probably a C and W. Divided by probability of W. Divided by the given, right? Because if I say given that it's a dude, well, how many people could it be? All the men. That's the number that's going to go on the bottom. So that's why you always divide by what's given. Okay. The nice thing is with chapter 5, it's going to reinforce some of the ideas from chapter 4 because 5 is all about probability distributions in general. So you're going to see a lot of the same probability ideas come up, but they're going to be a little more contained, a little less vague, a little more rigid. So let's see, where can we start here? Oh, they have a little bit of a review. Do you remember discrete and continuous? What was the difference between those two?
Discrete is a capital number, continuous is a scale.
Beautiful. So if I want to weigh something, I can be as precise as I want to be. 7.003942 pounds makes sense. But if I say I've got 3.829 doors on my car, that does not make sense. Doors can only have a certain number of values. That makes sense. That's why it's discrete. Whereas weights can have an infinite number of values that make sense. That's why it's continuous. So chapter 5 is all about discrete distributions to begin with. And then we start getting into continuous distributions in chapter 6. So here's the idea. I mean, you probably, I try to stay away from using the terminology too often, just enough so you get the idea of the words. Because a lot of times the ideas are so simple, but they're buried beneath all these words. So watch this. I'm going to show you the math behind what we do in this section works. Right? I'm going to show you why the math works. You're not going to have to do what I'm about to do for every problem, thank God. And I'll show you a reason why that's a thank God. But I want to show you why the math makes sense. So tell me, just say I get this sample data. I get let's see, 4, 6, 7. Okay. Again, I really want you to understand. I'm about to show you why the math in chapter 5 works. So everything I'm about to do, you're never going to actually have to do. I just want to show you why it works the way it does. How would you find the average of that list? How would you find, in fact, let's not even say sample data. Let's just say, think that population data. How would you find the mu? What would you do? Add them all up and divide by there. So could I be smart about adding them up? Aren't there 4 1s plus 2 2s plus 1 3 plus 3 4s divided by 10, right? Isn't that's what it is, right? I'm not tricking anybody. Not David Blaine over here. Is that too old of a reference? Is he still around? All right. Now, let me see. We would just do this. Over here, I'm going to do what we would normally do. And then I'm going to show you a different way to do this for when this list gets stupid big. Right? Because this is easy. Why would I do what I'm about to do? I'll show you. What would we do now? We would just say that's 4 plus 4 is 8 plus 3 is 11 plus 12 is 23 out of 10, which is 2.3. Right? How we doing? Hopefully I had it up right. 8, 11, 23. Yes. Yay. Is everybody cool with that? So that's done, but let me show you a different way we could have done it. And thank God we can do it this way because it's going to make chapter 5 so much easier. Could I do this? And of course you go, sure, Jeff. Math boy, you can do whatever you want to with all that. Right? And isn't 4 tenths 40%? So that's like 0.4, 40% of my mean is 1s, 20% of my mean is 2s, 10% of my mean is 3, and 30% of my mean is 4. And now, if you do that, of course you're going to come out to the same stupid numbers, the same stupid problem, right? So sure enough, this is 0.4 plus 0.4 plus 0.3 plus 1.2. Add them all up, and you get 2.3. So that should not be amazing. Please don't be amazed by that. What's really cool, though, is they're not going to give it to me like this. They're going to give me the data like this. Much like a relative frequency table. Hopefully that doesn't turn anybody off too much, but that's all this is. What is probability? It's percentages that are relative frequencies, right? So here they're going to give me, what would it be? 1, 2, 3, 4. That's my data. Not really. That's not really my data. I don't have a 1 and a 2 and a 3 and a 4. I have 40% 1s, 20% 2s, 10% 3s, and 30% 4s.